So let's now move on to discussing the statistical view of images. So we've talked about having a structural view of a local region of one image, but when we when we think about images, there is another way to think about images as collections of random variables. So this needs a little bit of a quick explanation. So let's say that I decided to do an experiment in which we're going to have an experimental space, and that experimental space simply consists of using a tape measure to measure the heights of individuals taking this module. So I get my tape measure, I ask all of you to be volunteers for this experiment, and I capture the height of individuals taking the module through a series of measurements involving my tape measure. So I get 1.6 meters for the first person, 1.7 meters for the second, 1.6 for the third, 1.5 for the fourth, and so on. And so I get a collection of measurements, and let's say that I have a finite number of measurements, so I'm going to say that my final measurement is 1.7 meters. Okay, so with this finite collection of measurements, I can of course look at the average height, or I could perhaps, because there are quite a few of you taking the course, I could also look at form a histogram of the heights that I've observed. So this collection of measurements is associated with this random variable, and I can either try to characterize fully the distribution of height. So a partial characterization of that would be doing something like constructing this histogram. So as my histogram of heights, so that's variable x, and this we're going to denote as h of x. Now, I can also look at the mean height, so I can try to summarize h of x with one number by just finding the mean of these values if I have n measurements. Okay, so that's pretty easy, and that's a single variable. But when we think about an image, the idea we want to think about is to bring in, to thinking about an image, multivariate statistics. So let's say, so extending this analogy of measuring height, let's say that I took second measurement, which is the weight of each person. So I have height, and I have height was x, wasn't it? So I have x, which is the height of each person, and I have, well, let's call it w, which is going to be the weight of each person. Okay, so now I have two variables, and if I want to characterize these two variables, I can treat them as a pair, x and w. So each measurement, or each person, gives me two measurements. So I get a pair, or if you like, a tuple from each measurement. Or if you like, let's call it experiment. So an experiment now involves the observation of two variables, x and w. So as you might imagine, I can do similar things so I can, the extension of a histogram would be a bivariate histogram, and that would mean that I effectively make a two-dimensional array. So I've got x along one axis, and I've got w along the other axis. So this is now this is height, and somewhat confusingly, this is not width, but this is weight. Okay, so and I can populate this. So effectively, I'd have a grid here, but the grid is not an image. The grid is a space of it's the measurement space. So my all of my measurements will fall somewhere into the space, and I can also accumulate measurements in this space, and I can make a bivariate histogram. Okay. Now I can also summarize. I'm not going to try to sketch a bivariate histogram. Well, let's say we could really smooth this histogram. It's gonna look, it's gonna have some kind of shape to it, and there is some correlation between x and w. So we would expect that the histogram is going to be, or it's going to have some orientation in this two-dimensional measurement space. Okay, now I can also summarize the measurement space. In this case, instead of computing a mean of only one variable, or average of only one variable over n observations, I would calculate the mean of two variables. Okay, so I have a mean for x and a mean for w. So that's all nice. That joint, what I showed you, that joint kind of histogram, is an approximation to what's called the joint probability density function of x and w. And when I have, if I now think about images, what I can do is I can focus on just, well, let's say that my image only had 2 pixels. Then I could do a similar thing for my image, which is that I could look at the intensities of pixel A and intensities of pixel B and do a joint histogram of the intensities of pixel A and pixel B, and convert that. The extension of that is the joint probability density function of intensities at pixel A and pixel B. We're going to come back to this in a second. I just want to introduce the topic first of all. Now, the catch that we have is that, of course, we don't simply have 2 pixels in our image. We may have an image that contains hundreds of thousands or millions of pixels. Here I've said that a typical image size is 512 by 512. I think we can laugh at that now. This figure was one that was used at the, maybe 20 years ago. That would have been a reasonable size for an image, or a typical size of an image. I've left this in here just so we can see how far things have come. Of course, you can quite easily acquire images that are of size, tens of thousands of pixels in, millions of pixels in size, or 10,000 by 10,000 is not common in a digital camera, but it's not inconceivable. Okay, so such an image, according to this statistical view, will contain 262,144 random variables. If you wanted to specify a joint probability density function for all of these variables at the same time, it's a very tough problem. But nevertheless, this is something that we think about doing when we consider very large data sets of very many images, and where we can use some tricks from machine learning to try to summarize the joint density function of all variables together. However, what we can do usefully in considering image processing is to introduce a statistical view of images, is to take pairs of pixels at a time and look at the joint density function between pairs of pixels. So in the same way that we can look at a histogram of a single variable, or summarize that in the mean of that variable, we can also look at a joint histogram of pairs of variables, intensities of pairs of variables in the image. But we can also summarize those through an extension of taking the mean, which is through taking something known as the covariance function. So that's what I'd like to introduce. But in order to understand that, we need to just formalize a few other things first, which I will now like to do. So another way of thinking about an image in terms of the number of pixels that's present in the image is to think about the number of degrees of freedom. If you were to think about each pixel in an image as giving you a degree of freedom in a high dimensional space. So a single random variable can be said to have 1 degree of freedom, 2 random variables, 2 degrees of freedom, and d random variables, d degrees of freedom. And we can represent these degrees of freedom by a space of d dimensions. And that's useful. And I want to very briefly come back to my analogy of asking each person in the taking this module to volunteer themselves to have their height and their weight measured, and for each person, or for each experiment or trial that I do, where one experiment involves taking the height and weight of one person, I can produce or I can represent that using a scatter plot in which I have x on one axis and w on the other axis, and each observation then becomes a point in this xw space. Okay, so this is xw space, and it is so each point and I think I'm going to adopt the term experiment rather than observation, because I think experiment is a little less ambiguous than observation, which sometimes refers to the variable type itself. So, for example, x might be in classical statistics, you often refer to x and w as being two different observations, even if they come from one person. So let's use the term experiment. So each of these, if I had 1, 2, 3, 4, 5, 6, so these are measurements from 6 people. Okay, so I have 6 experiments, and each of these points, which the point representation you would use in a scatter plot, but you can also think of each point as being specifying a vector in this xw space. Okay, now that concept of treating a pair of variables and, in fact, a triplet of variables, so we could have weight, height, and body mass index, or lots of other variables, of course, so we can make our experiments a lot more complicated. Each of those variables adds another dimension to this space. So, but we can still use we can still consider each point as being specified by a vector in that space. So, coming back to the case of pixels, we can then think about an image that contains 262,144 pixels as being a vector in a 262,144 dimensional space. And so there is an equivalence in the very simple operation of taking an image and flattening it out into one long vector and treating that as being, or treating the image as being a vector in a d-dimensional space. It's a very, very direct relationship. It's very simple. However, one thing to bear in mind is that when we unravel our image into this big long vector, we've lost the nearness of 2 pixels that might have been close to each other in the representation as a two-dimensional array, become far apart in the vector. Now that is, in some ways, it's just a housekeeping problem. It shouldn't concern us very much, but it does have some practical implications in terms of how we build efficient algorithms to process images. And I'm specifically thinking here about contrasting between a type of architecture used in neural networks called a multi-layer perceptron where you use very simple linear layers, which are really just flat organizations of neurons that look at everything from the previous layer, and convolutional networks which explicitly respect the spatial organization and spatial proximity that an image acquired with a camera has. So it's just something to bear in mind that becomes important later on. It's a point that I make in the next slide. Okay, so let's look at some jargon that crops up in thinking about images in a statistical manner. So a random field is usually something that describes a continuous or 2 or 3 dimensional function that is non-deterministic. And what that means is that if you perform one experiment to observe the random field, and then perform a second experiment to observe that random field. So just to remind you, a random field is one that varies as a function of spatial position. So it's some sort of, usually a scalar property that varies as a function of spatial position, like an image, or an image in continuous space. So a random field will, between observations, successive observations of that field, not necessarily taken at some sort of regular intervals in time, but just at different points in time, will, if it fluctuates, then you can say, in an unpredictable fashion, then you can say that it is non-deterministic. Or another phrase for that is that it's stochastic. If you have something like a stochastic field, then the implication is that it behaves like a random, just like the measurement variable we looked at for height, but this time it's as a function of, so you basically have an infinite collection of random variables. If we think about capturing an image into a discrete form, so we have an image as a collection of pixels, then you can describe that as a discrete random field. And there we modify our notation, and so you will find this sometimes in some of the earlier literature, and particularly if you come from a signal processing background, this will be familiar to you. If you haven't come from a signal processing background, don't worry. I'm just trying to connect the dots in as many ways as possible, for as many people as possible. We can try to summarize that random field, much as the way as we summarize the collection of height measurements by taking the mean. We can summarize the random field, discrete random field, by taking a mean. So we can estimate a mean field, which is as a function of spatial position. And we do that, strictly speaking, through taking or applying what's known as the expectation operator. So how do we think about the expectation operator? So you can sometimes think of it as an experimental average. However, it has a deeper meaning than that. So thinking about the expectation operator or expectation as being an average is a shortcut. In fact, the expectation operator has the underlying concept of being able to extend the number of experiments to infinity. So let's make this a bit more concrete by coming to the case of this stack of images here. And here, each of these images represents a different experiment. So experiment 1, this is experiment 2, this is experiment 3, and so on. Okay, so in this case, I've got n experiments. And now let's look at taking the definition of the expectation operator. So first of all, let's look at a single variable. Let's just talk about the pixel intensity at location A. Okay, if I want to know what the average intensity at that spatial location is. So let me make this a little bit more concrete, because let's think about a context in which the camera is fixed. So we don't have a moving camera. It's a camera that's, let's say, attached to a building. It's a security camera, and it's pointing only in one direction. So it's not roving around space. Okay, so we're gonna make that we're going to constrain the problem in this way. So at one location of pixel in the image, we are looking at one location in space. So we can ask the question, okay, what's the average value at that location in the image? So we do that, of course, by simply adding up the intensities at A over all these frames, these n frames, and simply dividing by the number of frames, n. Okay, so that's pretty obvious. However, the expected value of intensity at A is, strictly speaking, I should say it's by definition, the average intensity when the number of experiments tends to infinity. So in other words, we only get, our average only approximates the expectation of, or the expected value of intensity at A. In other words, E of A, with this fancy looking E here, if n tends to infinity. Now, of course, we can't conduct an infinite number of experiments, but we can very often conduct a practical number of experiments that is very large. And so we often ignore this subtlety about the expectation operator. By the way, if you have, of course, many of you have done the reinforcement learning course, and it's the same expectation operator. There's no difference here. The expectation operator in reinforcement learning is the same expectation operator we're talking about here, but the emphasis is that, the strict definition is that expectation means average an infinite number of measurements, infinite number of trials, if we were talking about this in the reinforcement learning context, which is also the context that we would use in the neuroscience, in speaking about neuroscience. So trial equals experiment, so I'm again just connecting the dots here for across different terminologies or different subjects. Okay, so now what we do if we were to compute the mean of a discrete random field, we get what's called the mean image. That sounds a bit weird. It's the average image. Okay, so that's what mu represents. So mu is not just a single variable, as it would be in that case of measuring heights. It's a function now of spatial position, so it's also an array, and we call it the mean image, or if it comes from a random field, we call it a mean field. Now, once we've done that, once we've got this definition of and we sort of think conceptually about how expectation works, which is that you take an average not over a single measurement, but you take an average over multiple experiments. So being able to have experiments that are considered to be independent is very important. Now, if we now want to extend the idea of characterizing a joint distribution of pixel intensities, we can do the following. So we can ask the question, okay, so this is what let's say that I know this is what the average intensity is at A, and I do the same operation and averaging through experimental space at B, so I know what the average intensity is at B. Okay, so this is partially characterizing our collection of images. I can now ask the question, if in one of the images of these experiments I observe, if in one of these images I observe that the value of A in that particular experiment is a bit higher than the average I've computed, which is down here, Okay, in this particular, let's say this particular image, which is experiment 3, what is can I make a prediction about whether B, or the intensity at location B, is higher or lower? So note the framing of this context. So, and I'll repeat that because I missed a bit on B. If I know that in a particular experiment, the intensity at image A is higher than its expected value, what is I'm going to use the term probability that the intensity at B is higher than its expected value? So in order to make some sort of sensible statement about that, what I need to know is how much knowing the intensity at location A in a single experiment might allow me to predict the intensity at image B in the same experiment, in both cases relative to the mean intensities at A and B. So another phrasing of that, if I think about the mean image as being kind of a baseline, okay, so sort of a baseline means, before I do something, just note what the normal situation is. In this case, it's just I take that to be the average intensity. So given the if the average or if the intensity in one measurement is higher than the average, is the intensity at the second location likely to be higher than the average, or is it likely to be lower than the average, or is there absolutely no ability to make a prediction or statement about the intensity at B? Where is this useful? So this sort of information is very useful if you want to do image compression. And so given a stack of many images, you sometimes want to try to reduce the amount of storage on disk or the amount of storage needed to transmit information from A to B. And so you're trying to exploit the correlation structure within an image. And that's what this information gives you. Okay, so that's the thing that we're going to look at next, is to look at correlatedness between pixels. And the best way of doing that is, one of the easiest ways to do that is to compute what's called a covariance function. And this should be, by the way, a discrete random field. So the definition of that is, and this looks like quite horrendous, but note that this is simply specifying one location, which is A, and this is simply specifying another location, which is B. And the definition of this covariance function looks horrendous, but all we do is, first of all, find, so let's think about the mechanics of this calculation. So what we're doing here in the mechanics of the calculation is taking a particular experiment, looking at what the intensity is in that experiment at some location A, but subtracting from that the mean value of intensity at that location A. Okay, so this is a deviation. That's the bit just in brackets here. So we're looking at the deviation from mean intensity at pixel location A. And this is the same thing, but so that's right, deviation from mean intensity at B. Yeah, so what we do is we subtract. So let's illustrate it on this diagram here. So let's again look at this particular experiment 3 here. I'm just going to zoom in slightly, or try to zoom in slightly. Not sure if that works. I think it's worked. Okay. So here we are, zoomed in a little bit. So we're going to take, in this particular experiment, we're going to take the intensity here. From that intensity, we're going to subtract the mean intensity that we've calculated at location A. And we're going to take that deviation and multiply it by the deviation that we calculate at location B. Okay, so we have a product. And then what we're doing is we're repeating that product calculation across all experiments. Okay, so in this one, we find the deviation from the mean. Here we find the deviation from the mean, and we multiply those together. And then we take all those products and we simply average them. Okay, so the calculation is dreadfully simple, even though it looks very complicated. In fact, you know, there are some past exam papers where I ask you to calculate the covariance function because I want you to connect the notation of expectation with the definition of something called covariance function, and to have an intuition about what it means if you were to be able to do it for a finite number of experiments. And then you just need to remember that you allow the number of experiments to go to infinity. Calculation becomes infinite as well, but conceptually you're doing the same thing. So that's a really important thing to get your head around, and because it makes the abstract concrete. Now the abstract is very important here because and the abstract really comes from the definition of the expectation operator, which is through effectively averaging an infinite number of experiments. But you can always approximate it by averaging a finite number of experiments. For the case of calculating the mean, you're simply averaging individual variables. For the case of calculating covariance, you're averaging the deviation, or rather, you're averaging the product of the deviation of multiple measurements. So it's really simple. But what does it tell us? Okay, so if knowing the intensity in one particular experiment, again, let's look at experiment 3, at A, gives us a strong ability to say what the intensity is at B relative to the mean that we've computed, then what we would find is that the magnitude of the covariance function for that pair of pixels would be large. So it could be, that magnitude could be large and positive, or that magnitude could be large and negative. So when is it large and positive? Well, why is it large and positive? Why would it be large and positive? So for example, if it's large and positive, it means that if the value in a particular experiment of intensity at A is bigger than the average, let me start that sentence again. So let's start from the case of the deviations. So if when the intensity at pixel A is higher than the average value, and in that pair of pixels, the location at B, the deviation is also higher than that value, then those two things when multiplied together give you a large positive result. If that is consistent across all of experimental space, in other words, across all of the pairs of A and B you look at, same location but across the different experiments, then you get a large positive value in your covariance matrix. If, on the other hand, an A being higher than the average suggests that B is going to be lower than the average, so you basically have anti-correlation, then you get a large negative values in your covariance matrix. So covariance can actually be either positive or negative or 0. So 0 if there's no relationship between the deviation at one location predicting the deviation at another location in a linear fashion, so they're decoupled, if you like, or linearly decorrelated, then the values of covariance for those pairs of pixels will be close to 0. So covariance is really useful because it tells us about relatedness of pixels, and therefore relatedness of spatial structures that might be present in our scene. Okay, so this is summarized in here. So large magnitude values tell you about identify pairs of pixels over experimental space that are strongly linearly correlated, and small magnitude values say there's little correlation. So this is useful for let's say for image compression and studying spatial structure in images. A white noise image is a random field and a discrete random field. So that's, I should also say discrete. Okay. If all possible pairs of distinct pixels are uncorrelated, in which case the covariance function has a very particular structure, which is that it's 0 everywhere for any pairs of pixels except for the locations A and B being on top of each other. So in other words, the same pixel, in which case your covariance function boils down to 0 everywhere apart from the diagonal elements, which are the elements A and B, so basically A and A, right? So where m dash n dash is equal to mn, you're looking at the same pixel, and so covariance then becomes the covariance matrix then becomes all zeros apart from the diagonal elements, where your you get the variance of intensity. So the covariance values give you the variance of intensity at the pixels of the image. Finally, there is often a bit of confusion between whether white noise is a white noise image is Gaussian or not. So a white noise image is not automatically Gaussian in nature. A Gaussian white noise image is a very specific type of image in which if you were to look at the distribution of intensities, they are uncorrelated with each other. So pixel intensities are completely uncorrelated with each other. But also the distribution of intensities across the image obeys a Gaussian distribution. And it is quite possible, in fact it is easy, to construct white noise images which are non-Gaussian. So please make sure you distinguish between the term a white noise image and a Gaussian white noise image, because the two are not necessarily equivalent. Okay, so covariance structure for natural images tends to be surprisingly similar for pretty much all images that make sense to the human eye. So there is quite a strong correlation structure. And I discussed this a bit more in the notes, but I'm not going to go very much into detail in the lectures, but you should read about it in the notes. The basic idea is that if you measure the covariance function between two pixels that are spatially close to each other, in the example I've talked about where the camera is looking at a scene and the relationship between the camera and the scene is fixed, and the scene kind of makes sense to us, it's not white noise, and it's not sort of chaotic, then what you find is that the covariance function falls off slowly as you move the pixels apart. So or as the distance between the two pixels you're computing covariance function increases, you find the covariance value decreases slowly. So there is, generally speaking, in images that make sense to us, there's quite a lot of local correlation between pixels, and that is the basis of being able to do good quality image compression. So that is reduce the amount of data storage that an image requires on disk, or that is required to transmit an image. Okay. Right, now we're going to take a couple of, I'm going to show you now, before I come to this, which is where you use, oh, by the way, let's do this first, and then I'll come back to a little demonstration of the mean image in a very particular context. Okay, so where do we use this random fields idea? So in occasionally we use these concepts in mathematical modeling of images, or trying to get a handle on the complexity of images, and particularly the thinking about an image as being an observation in a very high dimensional space. You can kind of use the you can use the statistical characterization to try to bound or make predictions about the behavior of a collection of images or a series of experiments involving the acquisition of images. And in particular, let's think about the context of an MRI scanner. So one of the things, it doesn't have to be an MRI scanner. It could be an ultrasound scanner, an X-ray scanner, whatever. One of the things that you find in medical imaging is that even if you image the same subject, exactly the same scene multiple times, because of the nature of the imaging process, where you generally are trying to put energy into the body and get some sort of signal out, you often want to operate in a regime in which you keep the amount of energy you put into the body relatively small, as small as possible. And therefore, your observations, your images, tend not to be as nice and clean as the images you might be accustomed to with your mobile phone. So what you tend to find in most medical images, is that there's a certain amount of measurement noise in every single image you acquire. So, and this is, again, even if it's exactly the same patient in exactly the same position, taken a few seconds apart, you're going to have differences from one scan to the other, which are just due to random sources of noise. Those sources of noise go all the way down to the level of Brownian motion and thermal noise and physiological noise. So when we construct or when we engineer an imaging system, we often want to know how much the noise changes from one scan to another, given that the scene is exactly the same. And one of the ways we do this is to use what's called an imaging phantom. An imaging phantom is a physical object. So it could be, so I could take this thing and make this my physical object. It's just a deck of cards. But I can stick this into some sort of imaging system and repeatedly image it, okay? And build up, therefore, an experimental space, and use that experimental space to characterize the noise level of my imaging system. How do I do that? Well, I go back to this stack here. Okay? So basically what I do is I repeatedly acquire images, and this time the scene, the thing I'm acquiring the images from, stays in exactly the same position in the imaging system, doesn't move, nothing else is changing. All that's happening is that I'm acquiring a series of images, but because I will always have measurement noise in my images, I'm going to get some small degree of variation from one image to the other. To characterize that deviation, what I do is I use two things. So I first of all use the mean image, because that gives me, hopefully, if the noise is fluctuating in both directions at any point in space. In other words, from the mean value across the stack, the noise deviation might be positive or negative from the mean in any individual experiment. Then when I average or compute the mean image or expected image for that, or approximate the expected image for that phantom imaging study, I basically converge to the noise-free view of what this object looks like when it's in the scanner. And then, to characterize the noise, all I need to do is to take the collection of images and look at the deviation of each of these from the average, and then I get a sort of a measure of the deviation of, or I get a measure of the noise distribution for that scanner. So, for example, I might just, if I just focus on pixel A, so just at that single location, I can create a histogram of the deviations of A from the noise-free case, or in other words, the average case. And that characterizes the degree of noise in individual measurements of my system. So this may bring up a question in your mind. So if you want to image a person instead, and you want to reduce the amount of noise you have, why not just take lots and lots of images? Well, the reason is that remember I said that in many cases you're putting energy into the body, and so you generally want to minimize the number of times you put energy into the body to get a measurement out. Plus, each measurement takes time to do. So there is always a trade-off between the degree of noise you have and the amount of energy you're putting into the system, or the time you're taking to conduct the measurements. Okay. So that gives us one example of how we would characterize noise. So we could use this idea of the experimental space on a phantom, or what's called an imaging phantom, to characterize the noise performance of a scanner. And it's one of the largest, is one of the more common uses of the mean image. In machine learning or in artificial intelligence, you can also, so one of the, all modern cameras now do face detection, but face detection in digital cameras actually started back in the 1990s, and the very first algorithms for face detection effectively detected the face by, first of all, building up an idea of what the average face looked like. And that was done by taking a stack of images of faces. I can't remember how many were used in the original study. I'll look it up. It'll come to me eventually. And computing the average face. So to do that, you kind of have to bring all the faces into spatial alignment. So the usual way that was done in the early days was someone would sit there with a mouse and select the tip of the nose for every individual, and so you register everyone according to the tip of the nose. And so in practice, the average face for these early systems turned out to be quite blurry apart from the tip of the nose, which was pretty sharp because that's where all the images were in perfect alignment. And then that created a template of what the average face looked like. You could then use that to detect faces in cameras using a very simple algorithm. So that's another place where this idea is used. This is basically just talking about the same thing. But now what I want to do to wrap up is to look at another example of where we can use this idea of averaging across observations, which is to be found over here. Oops. Okay, let's zoom that down. Okay, hopefully you can all see that reasonably easily. Is this visible or not? It might not be visible, so let me bring this into the frame over here. Okay, so this is not acquiring at the moment. Why is that? Okay, there we go. All right, so I think I've got capture now. Let me see if I can. Okay, great. So I've got capture working now, and let me now drag this back over to where it should be. And let's come back here. Okay, so I think we're now in the right place. Good. Okay, so this is a very simple example of a collection of experiments. Now in this case, it's a bit of a cheat because what's being done is I've got a static camera pointing at Exhibition Road, and this is Exhibition Road probably a bit more than 10 years ago, when you can see you can probably recognize where this location is, but it looks pretty different because the paving is all different. And actually cars move on both sides of Exhibition Road in this set of images. Okay, so each of these images is now an experiment. Okay, so I've got all these images here. I'm not sure why that's jumping up. It's probably a rogue image stuck in there. Okay, so you can see that there's people moving on the street. I think you can see there's a person there moving, and there's also vehicles moving on the street. Okay, now if I take this as a stack of images, so if I take this as a stack of images, and I now average across this collection of experiments, then what I end up with is the average image, which is shown, where's my average image gone to, which is shown here. Okay, so the average image, despite the fact that there are things moving back and forth in the scene, the average image has effectively averaged all those pixels out. So the movement has basically been averaged out, and what you're left with is just a view of the stationary objects on the scene. This is sometimes known as the background scene, and doing an average over many observations in which you have static objects and you have moving objects is one of the niftier tricks you've got in computer vision to do image processing. So it's a very simple technique, and it's basically just the expected image across this particular scene. Now, if I have this background image, then what I can do is, when I now subtract this from individual frames, and just to remind you, the individual frames are these things here, okay? If I subtract this from the individual frames, what's left is, for example, the objects that are moving in each frame. So if I subtracted the background from this, I would just get an image showing me the van. Okay, now that's really cool, and it's the basis for quite a lot of algorithms that are out there at the moment in computer vision. So here is a demonstration of applying that approach to do the detection of objects in a scene. So what we have is a very simple set of commands, and you could probably do this in about 10 lines of Python code. Not using anything sophisticated, just writing stuff from the start. You can do this in a really small number of lines of code. That's me, by the way, going to lunch. I'd forgotten that I'd set the camera up. Oh no, I hadn't, because I was looking for the camera on my way down. Now, one of the things about this technique is it created a lot of waves in computer vision in the very early, well, I would say in the 1980s, probably late 1980s actually. So you can see that in some cases it's not necessarily easy to observe certain people in the scene. I mean, you actually have to be paying attention to all parts of the scene to see, to note everyone who's moving back and forth. And indeed, this is such a sensitive technique that it's able to pick up someone inside that room, near to the window, or inside that building, near to the window, who moves, who basically comes into view in the window. In fact, there are people in a room and they're moving around inside that room. Okay, so this is capable of quite sensitive detection, and it's used in a technique known as tripwire detection. So the modern deep networks can work wonders, but actually sometimes to save energy, you want to trigger a deep network to look at a scene and say, hey, you've got this thing in the scene, and do that not continuously, which is very energy inefficient, but just do it when something is changing in the scene. This is one of the tricks that's used to achieve that. Okay, so I just want to pop back to the notes just to finish up on one thing. So I think there's not much I want to summarize. You can, of course, go back and forth in the lectures to gain a summary of what we've covered. We've covered a little bit of biological vision, and we've covered a little bit of preliminaries about image processing. But one thing I want to point to is that I talk here in this slide when I talked about statistical thinking, is that I want to come back to a sentence at the end of this, or a phrase at the end of this, which is thinking about a joint density characterization. So it's a probabilistic characterization, or characterization of the variation of the variability we have within images and the behavior, the joint behavior of pixel intensities in an image or pixel colors in an image. And we say given some conditions. So the given some conditions is important because you can do some really powerful things provided you constrain the problem that you're trying to deal with. So I want to take you back to some of the things I said earlier on about the early days of machine vision, where you have a camera sitting there looking at a bunch of bottles passing on a conveyor belt, and you have a light source. So these sorts of situations where you can constrain the conditions, and then and try to then take the images under those conditions and do something really powerful and do something useful, it becomes easier the more you can constrain the conditions. And so even today, our deep networks can work wonders, but they work wonders particularly in the context of medical imaging or in biology or in science, in places where you don't have massive amounts of data. You can do wonders with image processing if you can constrain the conditions of imaging. And so that's something that I want you to keep in mind. And there are also some really deep things around that, such as looking at joint density functions versus, or joint probability density functions versus conditional density functions. Now, both of these are things that we're going, conditional density functions is something we're going to consider in Chapter 2, but also we're going to consider some of the techniques that I used to do that object tracking that you saw with the red boxes around moving objects. We're also going to explore some quite intuitive algorithms in Chapter 2. And those intuitive algorithms actually come from considering the notion of spatial connectivity and doing that in a very specific context of binary images, where we only permit ourselves to have two intensity values in an image. So we're not really looking at joint distribution of intensities anymore. We're actually looking at just two intensities, so the joint density thing becomes easier. And we consider binary images.